Alright, so today I'm going to talk to you guys about the Sn1, Sn2, E1, and E2 reaction mechanisms. So first I'm going to show you what they look like. So the Sn1 and Sn2 are substitution mechanisms. So you start with, the R means you can have anything. Any carbon, bromine, chlorine. And it's going to react with something in the X and the Z will just switch for substitution. Now with the elimination, when they react together, the X is going to go away, but it turns into a double bond at the end. I'll explain more when I show you guys. So for the substitution, I'll start with the Sn2 because sometimes that one is easier than Sn1, just to explain it. So the Sn2 is a one-step and it's bimolecular. So it requires aprotic solvents and is sterically unhindered electrophile. The rate law is K, nucleophile, and electron. It requires a great leaving group and a strong nucleophile. There's inversion of stereochemistry, which is R to S, S to R, or RS to SR, or SR to RS, and requires no rearrangements. The substrate is primary or secondary, tertiary, but usually you won't ever see a tertiary reaction. And here's what they look like. The primary, any carbon or whatever is on the very end, which is the strongest, most stable. The secondary, you see that there's an H right here with any carbon or anything, and then for the tertiary it looks just like this one, but that's also a carbon here. So I did an example, and you have a bromine right here, and this is any carbons. The shaded wedge here is a wedge, and that means it's coming straight at you. The dash marks means it's going away from you. So if you were to look at it from this way, the CH3 would be on your left and the bromine would be on the right. If you were looking at it from right here, right up here. So it's going to react with an Na3. The N3 is going to attack here, and the bromine will leave, and it's going to turn, the N3 is going to take bromine's place, and you're going to get this product with N3 on a wedge and CH3 going away. For an Sn1, it's two steps and it's unimolecular. You need a very stable carbocation. The rate law is, it depends on any concentration of an electron. It has a great leaving group, any nucleophile will work, a protic solvent, it will be fastest with a protic solvent, and racemization. Substrates, it goes from benzylic being the most stable to allylic. The allylic and the tertiary are pretty much the same. You have the secondary and then a primary, but you'll never see a primary with Sn1. So for the benzylic, you have the benzene ring with a positive right over here. The allylic, the allylic and the tertiary are kind of, there's two different ones because you can have the plus on one side and the positive on the opposite side, but they're the exact same molecule. The primary, it has 3 carbons and it's positive, so that's why there's 3. This one, you have the 2 carbons in the positive and another one here with a positive on this side, but you won't ever see this one. So for the Sn1, sorry, I chose H2O for it to be reacting with. So you have to start out first with the bromine leaving, so it's not there anymore. It goes away, but now you have to rewrite it for the carbocation, which makes it positive right here. And so that means the H2O is going to attack right here to make the positive go away, because you don't want a positive in your final product. And it's going to be either the it's going to be with the CH3 on the wedge and the OH2 on the dash marks going away from you, or the OH2 on the wedge with the CH3 going away from you. And I'm going to say we're using double-headed arrows, which means 2 electrons are going, both of them, like right here. Both of the electrons are attacking. But if you ever see an arrow that's just half, we call that a fish hook, and it's only bringing 1 electron with it, just 1, so just 1 dot. And you'll see somewhere that sometimes it'll be like a Br with a bromine with just 1, and that's because they used a fish hook. So yeah. Sorry for my sniffles, I've been kind of sick. So for an E1, which is the elimination mechanisms now, it's a 2-step, and these are usually alkenes. It's only affected by concentration of an alkyl halide, which is your starting material, a carbocation intermediate, which means you just have to draw your carbocation, make it the most stable, and then you can finish off your product. So instead of a nucleophile, we use a base, which is a proton acceptor. So we need a strong base, and we'll see that the Zaitsev is the most stable, which is a Zaitsev product. Your substrates for both E1 and E2 are the tertiary, secondary, and primary, but you'll never see a primary for E1 or E2. So for this example, I chose H2O and heat. Heat makes the E1 go through the fastest. So first you need to have your bromine leave so you can draw out your carbocation. I drew in the H's because for me, at least, it makes it easier to see where the H's are, and it just helps. So I drew it out, and you have 2 H's here, and you're going to have 1 H over here. Your OH2 is going to attack this H, and then it's going to move from here to the section here with the positive, so the positive goes away. And that's going to create a double bond. For E1 and E2 reactions, you're always going to have a double bond in your product. So since the positive charge was right in here, that's where the double bond is going to go, because this moves up to here. So it looks like this. And your Zaitsev product, this is the Zaitsev product, which is the most stable this product can be. Now for E2, it's a 1-step. There's no carbocation, but there's going to be sterics, and the Hoffman product is formed when using a bulky base. And the Zaitsev product is produced if you use a small base, and your substrate is going to be the same as E1. The tertiary is the best, and then you have your secondary, and you won't ever see a primary. And if you see a primary, it's going to be very weak. So I used an O-tert for my reaction. And since it's one step, your bromine is going to leave, and the O-tert is going to attack the H up here, just like I said up there. I draw in the H's and it makes it easier for me. It's going to attack the H's, this right here, and it's going to move to this intersection with the CH3 and the bromine, and your bromine is going to leave. So your product will have a double bond again, but this one is the Hoffman product. Now, I have some examples so I can explain it some more. So number 1, we see that it has a strong nucleophile and a strong base. And it is secondary. So all that information means this is an E2 reaction. So that gives us a way how we can figure out how to solve this. So let me redraw it. Your O negative is gonna attack. Let me draw in the H's since that works for me. I'm gonna have 3 H's on this side because all carbons have 4 bonds, and since this is 1 carbon, there's gonna be 3 H's. This wedge means and there's nothing attached, so that's just a carbon, but it's coming at you because it's on a wedge. So your oxygen with your negative charge is going to attack this H because it's opposite of your chlorine that's coming at you. It's on the opposite side of this wedge, so that means it's going away. And then it's going to go from this bond here to where the chlorine is. And your chlorine is going to leave, which gives us this product. And this is a Zaitsev, which is the most stable that we can have. So number 2, we have a bad nucleophile and a strong base. Because the DBU, which means it's a E2 reaction. So just like the first one, I'm gonna redraw it again. There's an H here. Your DBU is going to attack this H right here. This H bond is going to attack this wedge. I'm sorry. This has an OTOS on it. And then the OTOS is going to leave, which gives us this product. Just like that. Alright, so this next one, we have chlorine and a benzene ring. So this right here is protic. Strong nucleophile. Sorry about that. A strong base. So there's many options it could be. Now, this is secondary. So that means it is E2 again. Alright. So I'm going to redraw it. And the dash marks that have nothing on it is just like a carbon. Alright, so I'm gonna draw in the H right here, and your O is gonna attack the H here, and then this H bond is gonna attack the chlorine bond right here, and your chlorine is gonna leave, which gives us this product right here with the double bond. That bond right here moves to make a double bond. Sorry, that double bond is not very good. Alright. And then another example I have, I messed up on this one, my bad. We have a strong nucleophile and a strong base, which makes this an E2. Alright, so sorry about that. There's an H on a wedge right here. You don't have to draw in the H's, but it makes it way easier to solve when you know where the H's are. Your base is gonna attack the H right there, and then from the bond here, it's gonna attack this bond with the chlorine going away right there, and your chlorine is gonna leave again, giving us this bond or this product like this. The double bond is here. We still have the wedge, we didn't touch it, and now we have that. Alright, just 4 more examples for you. Alright, so this is acetate, and it's a strong nucleophile. Nu is another way to show nucleophile. It's a shorter version. We have a strong base. It's secondary, and it's aprotic. So that gives us an Sn2 bond, or mechanism, that we're going to use to solve. Okay. So with it being Sn2, it always makes it easier for me to redraw what you're gonna be working on so you know you have enough room. Your acetate is gonna attack the wedge that the bromine is on, and then your bromine is the leaving group, so your bromine's gonna leave. Oh, my bad, it's because it's your bromine. And your acetate is gonna take its place, but it's gonna be on dash marks. Just like that. Next you have this one. Alright, so this is aprotic. It's a strong nucleophile and a weak base. It's primary, so that makes it another Sn2 bond. Sorry, I keep saying bond. It's mechanism. I have bond in my head right now. So, but this one I'm just going to keep it like this. Your N3 right here, which is just nitrogen, negative, that's why it's N3, is going to attack these carbons right here. Right here. And then from this bond to your OTOS is going to leave, making this product. Your O is still there, your oxygen. And then your 3 nitrogens take its spot. Next, we have a weak, these two are on, both are on wedges. So this is a weak nucleophile and a strong base. Making this another E2 reaction. I'm gonna go ahead and draw in my H's for this one. An H here will be on a wedge, and then you'll have an H on dash marks. So an H, your base is gonna attack the H on a wedge right here, and then from the wedge it's gonna attack where the wedge for the bromine starts, right here, sorry, right there, and then your bromine is gonna leave, making this product with your double bond and your OH. Okay. Now the last example I have, it's the exact same as number 7, but your OH is on dash marks. But everything else is the same. So you still have a weak nucleophile and a strong base. So it's still E2 reaction. And then I'm gonna draw in the H's again. like that. So your H, just like the first one, is going to attack the H here on the wedge, and the wedge, this bond is going to attack the bromine, and then your bromine is going to leave, giving us the same answer as number 7. That's all I got.